Hey there, science fans. Ever noticed how honey takes its sweet time flowing compared to water? That's because honey is more viscous. It resists flow more. Viscosity is all around us, from the ketchup we coax out of the bottle to the engine oil keeping our cars running smoothly. Imagine diving into a pool of honey versus a pool of water. Which one would you struggle to move through? That's right, honey. It's all about how easily a fluid flows under stress. Low viscosity means easy flow, like water. High viscosity means slow flow, like you guessed it, honey. Think of viscosity as a fluid's internal friction. Just like rubbing your hands together creates heat due to friction, fluids experience resistance as their layers move past each other. The stronger the internal friction, the higher the viscosity. So the next time you're waiting impatiently for that ketchup to land on your burger, blame it on viscosity. But hey, at least now you know why it's taking its sweet time. Stay tuned as we dive deeper into the fascinating world of viscosity and uncover the secrets behind falling objects. Let's get down to business and define viscosity like the science rock stars we are. In simple terms, viscosity is a measure of a fluid's resistance to flow. It's all about how sticky or gooey a fluid feels. Think of it like this. Imagine pushing your hand through a swimming pool versus pushing it through a tub of peanut butter. Your hand moves easily through the water, but the peanut butter puts up a fight. That resistance you feel in the peanut butter is its viscosity at work. Viscosity is directly related to the friction between the layers of a fluid as they move past each other. This friction is what we call drag force. The higher the viscosity, the stronger the drag force, and the slower the fluid will flow. Viscosity is a crucial property in many fields, from manufacturing and engineering to medicine and even cooking. Understanding viscosity helps us design better products, optimize processes, and even predict how fluids will behave in different situations. Now let's talk about objects falling through fluids. Ever wondered why a feather takes its time descending while a rock plummets to the ground? It's not just about their weight, but also about the fluid they're falling through, and something called Stokes' law. Stokes' law is a physics principle that describes the drag force experienced by a small spherical object moving through a viscous fluid at a constant speed. It's like a secret code that helps us predict how fast or slow an object will fall based on the fluid's viscosity and the object's size. Here's the formula that unlocks the mystery Fd equals sign, 6 perv where Fd is the drag force, pi is a mathematical constant, approximately 3.14159, eta, Greek letter eta, represents the fluid's viscosity, r is the radius of the spherical object, v is the object's velocity, speed in a specific direction. This formula tells us that the drag force increases with higher viscosity. Think of honey versus water. A marble will fall slower in honey due to its higher viscosity. Larger object size, a bigger marble will experience more resistance than a smaller one in the same fluid. Faster velocity. As the object falls faster, the drag force increases. Stokes' law helps us understand the behavior of tiny particles in fluids, from dust settling in the air to red blood cells flowing through our veins. It's a fundamental principle with applications in various fields, from environmental science to biomedical research. Section 5. Stokes' law in action, from sedimentation to tiny charges. Stokes' law isn't just a theoretical concept confined to textbooks. It has real-world applications that impact our lives in countless ways. Let's explore a few examples. First, sedimentation. Ever wondered how geologists figure out the age of rocks and sediment layers? Stokes' law plays a crucial role. By studying the settling rate of particles in a fluid, they can determine the size distribution of sediments and understand how they were transported and deposited over time. Second, viscometers. These nifty devices measure the viscosity of fluids using, you guessed it, Stokes' law. By measuring the time it takes for a sphere to fall a certain distance through a fluid, we can calculate the fluid's viscosity. Viscometers are essential tools in various industries, from food processing to paint manufacturing. Third, the Millikan oil drop experiment. This classic experiment used Stokes' law to determine the electric charge of a single electron. By balancing the downward force of gravity with the upward force of electric attraction on tiny charged oil droplets, Robert Millikan could calculate the charge of an electron with remarkable accuracy. These are just a few examples of how Stokes' law helps us understand and manipulate the world around us. From studying the movement of microorganisms to designing efficient drug delivery systems, the applications of this fundamental principle are vast and ever growing.